Okay, so example, it give you a what I call a toroid here, a circle toroid with winding 400 turn and current that you don't know. So the question is find the current so that a magnetic flux of 4 times 10 10 power of negative 4 Weber can be produced inside this magnet, okay, inside these materials. The probability of the material is given as 1.818 10 minus 3. Okay, and okay, so to find the current here, so what you need to do is actually, you know that the relationship of the current is actually depend on the force. Okay, so the force, the N is given as a 400. So you need to actually get the force value or other values. Okay, so for this example, the first step is to calculate the flux density. Okay, so the flux which is given, okay, and then the cross section is also given here. So from there you can directly obtain the flux density. Okay, so from the flux density you can actually obtain the magnetizing force, which is H. Okay, and we can obtain the H is equal to this one, and from this I can see that relationship now is actually, which is Ni, and this one also, this Ni also related to the HL. Okay, so right now we have the H and we also have the L. Okay, so next is actually you can get the I. So this is the relationship that I have told you earlier. Okay, so H is already calculated, multiplied with the length of the materials over the number of turns. So the current that required is around 44 milliampere. This is the second example. So find the flux if the flux density is 1 Tesla. And then the current in the coil and the magnetic field strength in the air gap and in the magnetic core. So as you can see here, the circuit is actually a series circuit with two different reluctance. So I can write down like this. Okay, so reluctance of the what I call the core and the air gap. Okay, and then this is the Ni. So we need to find the flux. Okay, but it's also given B. Okay, B has been given already, which is 1 Tesla. Okay, so you can always start with the finding of the flux because you have already beta here. Okay, so the flux is B multiplied with the cross section. Okay, so you have B multiplied with A, so you have flux here. So from that, okay, you can calculate your SC. So your SC has been given, which is L 0.3 over the mu R, which is mu R multiplied with the mu naught multiplied with the cross section, okay, of the material here. So you will have your SC, okay, and then the second one is the SA, the SA gap, which is the L, the length of the air gap, which is 0.005 meter, and the air gap permeability is mu naught multiplied with 1, mu R is 1, multiplied with the cross section of the air gap, which is similar to the cross section of the material, which is 9, 9. Okay, so you will obtain SC and SA, and then you have already got the value of the flux. Then using this formula, which is Ni is equal to flux SC plus flux SA, then you can get Ni. Okay, so from Ni, so finally we can have I, which is over N, so you can get the current. Okay, so as shown here in this solution, so the first one is to calculate the flux. Okay, you obtain the flux. Okay, and then you calculate the reluctance values for the air gap, which is this one is the for the S, what we call, this one is the air gap. Okay, sorry, and this one is the for the core. Okay, so you can get the value of this one as equal to this, and this one equal to this, and then you know that from here you can finally get the current, which is 0.8 ampere. And the second question is on the magnetic strength. So the magnetic strength is a simple, straightforward, where the intensity, so the flux density is the same for all materials, because the flux density is the same. Okay, because the same flux flows, flows inside the same circuit here, so it's remain the same. Okay, so for the core, the magnetic force is around 11.7, while the magnetic strength, okay, magnetizing strength is around 7.96. Okay, and then this is example 3. So example 3, I will actually explain a little bit further. Also, I also have done some video explaining on the solutions. Example 4 also, I have done the video and also the solutions, so we will discuss during class. Example 5, so I leave it to you to actually solve it by your own practice, okay, by your own. And example 6 also, I have also done it for you, and I also have the video and also the solution, so we discuss during our class. Example 7, I will leave it to you to actually try it. So it's been given, it has the answer, so you can try. So for the series parallel magnetic circuit, so actually you can use what I call the mesh current analysis. Okay, from the Kirchhoff law, the Kirchhoff current law, we always know that okay, when we have two branches, so we can calculate the theta r, the flux. Okay, the flux 1 is equal to the summation of the other flux of for each branch. Okay, and from the mesh current analysis, you can always calculate by using this equation. So the field is equal to the drop here, voltage drop, or what I call HL. Okay, multiply with the H3 here. Okay, and L3. Okay, and for the second loop is H3L3 is equal to H2L2. Okay, and then if you have a series parallel magnetic circuit, for example, like this, okay, so please ensure that you need to know that for this type of circuit, where your MMF is actually at the center, please note that you need to actually add the the reluctance for this branch. Okay, and this is for the first and second branch. Okay, so sometimes students forgot to include also the reluctance of this branch. And then this is the series paramagnetic circuit with air gap. So this is the equivalent electrical circuit here. So as you can see, you need to add, you have for this branch, you have two different reluctance that for the core at this branch and the reluctance of the air gap. Okay. Okay, so I think we finish here and we will stop, we will continue on the next video on the core losses. Thank you very much.